All right, so hello everyone and welcome to today's lecture. Today we're going to be continuing to talk about prefix sum. Let me start by reviewing what we covered last time, and then we'll proceed to cover today's content. So this is part 2, but let me quickly switch to part 1. Okay, so last time we started talking about scan, and we said scan is an operation where, wait 1 second, let me get the pointer. And we say scan is an operation where we take an input array and we apply some associative operator to get the output array, where every element in the output array is the operator applied to the corresponding element and all preceding elements in the input array. And for an exclusive scan, it's the preceding element, but not the corresponding element in the input array. And what we did last time is we said that because scan requires a sort of because scan requires sort of synchronization, as we will see, across threads as they are performing the parallel scan. What we focused on last time is doing a segmented scan where every thread block does a scan of its own segment inside of the input array. And we said that later on, which is today, we're going to worry about how to consolidate these segments. So we will continue optimizing the block-wide scan today a little bit, and then we'll move on to talk about how to consolidate things across the arrays. So looking into a single block-wide scan, the question is how to do it. And we said that the way that we do it is by overlaying multiple reduction trees. So we saw reduction before, and we said that the way that we can do a parallel prefix sum is by doing multiple parallel reduction trees for multiple elements in the output result. And of course, we get a lot of the other output elements as a byproduct. And by overlaying these reduction trees, we are able to get a fully scanned resulting array. And the scan is called the Koji-Stone parallel scan. It also has other names in literature. We call it Koji-Stone after the Koji-Stone adder, which came up with this technique. So to parallelize this, what we can do is we can assign we can assign a thread to each element, and that thread is going to be responsible for evolving that element from the input to the final output throughout the scan process. And of course, like we did with reduction, we can put these intermediate, we can, since we keep reading and writing from the segment to update it and evolve the elements, what we can do is we can put that in shared memory. Okay, so this was our first implementation. But one thing we observed about this implementation is that we had two sync threads inside of our loop. One of the sync threads was enforcing a true dependence, but the other sync thread was enforcing a false dependence. So what we did in order for us to get rid of the sync threads that was enforcing a false dependence is apply double buffering. So the idea is that the reason we need the first sync threads is because the same element x1 over here was being read and written by this thread and was being read by this thread. And because we have multiple threads accessing the same element and one of them is a write, we needed that sync threads to make sure that we finish reading before anybody writes. We can get rid of that by using double buffering, where we use a separate buffer each iteration for reading and for writing. Okay, and we only need two buffers because once we finish reading a buffer in an iteration and we write to a new buffer, the new buffer becomes our input to the next iteration, and we can repurpose the original buffer as the output of the next iteration. So we keep swapping the buffers, and we need two buffers in total. So this was one of the optimizations that we implemented to reduce synchronization. We also looked at using warp level primitives to further reduce the synchronization. And we know that threads in the same warp can communicate with we learned that threads in the same warp can communicate with each other and synchronize with each other in a way that is faster than threads in different warps. So we took advantage of that by decomposing our block segment into a segment for each warp, having each warp perform a scan of its own warp level segment, and then taking the warp, combining the warp sums, scanning those warp sums to have the scanned warp sums, and then later on, every warp will take the element that represents the sum of all the elements in the previous warps and add that element to its own result. Okay, and this is how we were able to segment the scan across warps and then combine the results of 3 different warps. You can probably guess that we're going to do something similar across blocks. So in this case, instead of having async threads on every iteration of our prefix sum, we only need async threads to separate the first warp scan phase from the second warp scan phase, and then to separate the second warp scan phase from the add phase. In other words, warp 0 has to wait for all the previous warps to finish scanning their segments before it scans the sums, and then all the other warps have to wait for warp 0 to finish scanning the sums before they add. So we just have 2 sync threads in the whole implementation. So this is where we left off last time. Any questions about what we covered last time before we move on to today? Everything's clear? Yes. So someone asked me to repeat what I just described on the slide. So the idea of dividing the scan across warps is every warp will perform its own scan of its own segment. Now, later, what we want to do is to get the final scan result. Warp 1 has to add to its elements the sum of the elements in warp 0. Warp 2 has to add to its elements the sum of the elements in warp 1 and warp 0. Warp 3 has to add to its elements the sum of the elements in warp 2, warp 1, and warp 0. So what we do is each warp is going to contribute its warp sum to an array in shared memory. And then we're going to have one warp scan those. And when one warp scans those, now the first element is the sum of the elements in warp 0. The second element is the sum of the elements in warp 0 and warp 1. The third element is the sum of the elements in warp 0, warp 1, and warp 2. So then each warp now is going to take the element in these scan sums that represents the sum of the elements in all the previous warps, and it's going to add it to its own elements to get the final result. Is that clear? Yeah. So to clarify, for example, warp 3 needs the sums of the elements in warp 0, warp 1, and warp 2. The sums of the elements in warp 0, warp 1, and warp 2 are written here, warp 0, warp 1, and warp 2. And then when we scan these, the sum of these 3 elements is now this value over here. So this is the value that we are taking to warp 3 and adding to all the elements inside of warp 3 to get the final result. Right? Clear? Any questions? Okay, so if there are no questions, then today we are going to continue talking about prefix sum. And in particular, I want to comment on something related to the previous the Kojistone parallelization approach that we discussed, and that's related to work efficiency. I tried, but it doesn't seem to be. It doesn't seem to be working. I don't know why. Yeah, sure. Please go ahead and proceed on. Okay. Okay, so what is work efficiency? So we say that a parallel algorithm is work efficient when the parallel algorithm does the same amount of work as the corresponding sequential algorithm. Okay, so for example, in vector addition, when we do a sequential vector addition versus a parallel vector addition, the parallel vector addition does the same number of add operations as the sequential vector addition, right? So in this case, we say that the parallel vector addition is work efficient. The number of operations done by the parallel algorithm is the same as the number of operations done by the sequential algorithm. And in fact, so far, all the different parallel implementations that we've seen have been work efficient. When we parallelized convolution, when we parallelized stencil, when we parallelized matrix multiplication, for all of these, the number of arithmetic operations that was done by the parallel algorithm was the same as the number of arithmetic operations that was done by the sequential algorithm, right? Okay, but let's look at scan. Let's talk about the work efficiency of scan. So how many addition operations does the sequential scan perform? It does n operations, right? So sequential scan performs n operations. So what about the Kojistone scan? How many operations does the Kojistone scan perform? Well, let's reason about it. So we have log n steps. In each step, we are doing, in the first step when the stride is 1, we are doing all the threads work except one of them. So we're doing n minus 1. when the stride is 2, we're doing n minus 2 operations. When the stride is 4, we're doing n minus 4 operations. So in general, we have log n steps, right? And for these log n steps, every step does n minus 2 to the power of the step iteration number of operations. So if you work that out, it comes out to n minus 1 plus n minus 2 plus n minus 4 up until n minus 2. And this comes out to n log n minus n minus 1, because n plus n log n times n log n, and then 1 plus 2 plus 4 plus da 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 plus n over 2 is n minus 1. Sorry, n plus n is n log n. So this comes out to O of n log n. So the number of operations performed by the parallel scan is O of n log n, whereas the number of operations performed by the sequential scan is O of n. Okay, we are performing more arithmetic operations in total in order to be able to parallelize the scan operation. And because of this, we say that this algorithm is not work efficient. Okay, now what's the problem with an algorithm being not work efficient? Okay, so somebody said we'd rather doing it sequentially than parallelize it. So maybe, right? You know, if we parallelize it and we're getting it to go faster because of the parallelization, right? Then maybe that work inefficiency, those redundant operations, are a price that is worth paying in order for us to.
But maybe they counteract the speed up of the parallelism.
So won't it counteract the speed up of the parallelism? So let's think about this, right? If I have n operations, if the parallel algorithm does n log n operations, but I parallelize it across n threads, then that's okay, right? Because that'll take me log n steps to finish. So when I parallelize scan, if I actually parallelize, if you know all these threads are actually running in parallel, okay, then that parallelization is worth it, right? But if if I'm doing these n log n operations across log n threads instead of using n threads, then in that case, what's going to happen is the hardware is going to end up serializing my thread blocks instead of running them in parallel. That is the case where the work efficiency starts to hurt us, because if I don't actually run in parallel, then I'm doing these extra operations in order for me to get the parallelism, but then I don't parallelize and I end up doing these operations sequentially. So I could end up taking longer than the sequential algorithm because there are more operations that I need to do. Is this clear?
Professor, so you mean for the second case, in case we assign log of n threads in the block or grid instead of n?
Yes, hypothetically, yeah. Now, of course, what would that implementation look like? There's every thread is going to be responsible for multiple things. You can do it efficiently, you can do it inefficiently. But the principle is that if I actually run all of these operations in parallel, right, then or if I actually have n threads doing my computation, then the parallelization, the work inefficiency, the redundant operations are a price that is worth paying. But if I don't actually have n threads doing the computation, then that work inefficiency can come back and hurt me, because what would happen is the thread blocks would get serialized instead of all running in parallel. But now the thread blocks that are being serialized are doing n log n operations as opposed to n operations. So that could end up hurting performance. Is that clear? Yes. So yes, somebody asked me, does this take into account dependence between threads? So yes, because when we did this computation, we said n log n, where log n is the number of steps, right? So that log n number of steps is kind of capturing the fact that we have to iterate and synchronize in between threads, right? So obviously, if I had an input of size n, using this algorithm that we developed, we cannot parallelize across more than n threads. So the log n is the minimum serialization factor that we're going to have, correct? But we can if we parallelize across fewer than n threads, that's where things start to hurt. And that's the example where I pay this cost to have 2 thread blocks, but then they get serialized one after the other. So I've paid these redundant computations unnecessary. Okay, great. So what do we do when when there's some kind of price that we pay to parallelize something, but then we don't actually get the full parallelism? What can we do to? Right, exactly. So one optimization that we can apply to deal with this work efficiency issue is thread coarsening, right? With thread coarsening, if there's some kind of price that we pay in order for us to parallelize a computation, but we don't get all the parallelism that we want, right? We can reduce that price by applying thread coarsening, okay? So the idea here is that we're paying work efficiency, we're doing redundant operations to get parallelism. If we are not getting that parallelism because we're extracting way more thread blocks than the hardware can run simultaneously, what we could do instead is we can do thread coarsening, where we can have every thread do its own sequential scan of a segment of elements, right? We launch as many threads in it as can run simultaneously. Each one does a segment, scans a segment of elements. The sequential scan is going to be work efficient, right? And then after that, we can do a parallel scan to be able to scan across threads only, but not within the segments of threads. Okay, so let me elaborate on this. So here we said that parallelization incurs the overhead of lowering the work efficiency. We also have the barrier synchronizations, and when we parallelize, we have all these barrier synchronizations that we incur in between the different steps. So if the resources are insufficient and the hardware is actually serializing these thread blocks, then the work inefficiency and all that synchronization, like just like we saw in reduction, for synchronization we saw in reduction, but reduction is not work inefficient. So all that redundant computation synchronization is paid unnecessarily. So what we can do instead is we can apply thread coarsening, where we can have every thread sequentially scan a segment, and the sequential scan is work efficient, right? And then we can and then after that, we only have to scan the partial sums of the threads in parallel. Okay, let me illustrate what that looks like. So what we can do, if this is our block segment right here, we can divide that block segment across threads. Every thread will do a sequential scan of its segment. And while the threads are doing a sequential scan of their segments, right, there is no synchronization. And also there's no work inefficiency, right? If a thread has a segment of size n, it's going to perform n operations to scan its segment. So this stage does not incur any synchronization or work inefficiency. After each thread scans its segment, what can we do? We want to consolidate the segments of the different threads. So how do we do that?
We do something just like warp level scan. So
right, exactly. We can. So people in the room said, and people online are saying the same thing. We can do something similar to what we did with the warp level scan. We can have every thread contribute its sum. After that, we can do a block-wide parallel scan to scan the sums of each of the individual threads. And then after that, each thread can go and fetch the sum that corresponds to the previous threads, add it to its own segment, and that gives us the full scan block segment. Is that clear? Any questions about this? How's it different from the warp? So somebody asked me, how is this different from the warp implementation? It's the same strategy as the warp implementation, but at the thread level. So here what's happening is we're taking the block segment, we're segmenting it across threads. Every thread is doing a sequential scan, then contributing one sum. And now we do the block scan. Inside of this block scan, we're going to take these thread sums, segment them across warps, have every warp do its own scan, right? So in this block scan right here is what we implemented last class, right? So inside of this block scan, we're going to do the warp level segmentation, have the warp scan, then have one warp scan the partial sums, then go back and add them, then come out of this and do the thread level additions. Is that clear? So
the difference,
kind of a recursion happening.
yeah. So the difference from last implementation is that here the segment, it's not 32 like a warp size, right? It can be further.
Right. The thread segment is going to depend on the coarsening factor, right? We can decide how big the segment can be, right?
So
But
that's
this is
only
not
difference.
replacing the warp scan. The warp scan is still happening. It's happening inside of this block level scan, and we'll see that when we do the implementation.
Yes.
Was there another question online? Okay, so let's go and implement this. Okay, it's quite elaborate. Okay, so this is the implementation that we left off last time. If you remember, we implemented a warp scan, and then we implemented a block scan. And then in the kernel, what we did is we simply had every thread load a value, do a block scan of that value, write that result to the output, and then do the partial sums. So this time what's going to happen is every thread is going to, we're going to load, the block segment is not going to be as big as number of threads. It's going to be much larger than that. So we're going to have to load that entire block segment into shared memory, and then have every thread scan its own segment inside of the shared memory. Okay, so let's do that. First, let's define some coarsening factor. There, I'm going to define a coarsening factor. Let's make it 4. So we're going to give every thread a segment of size 4, right? So every thread is going to scan 4 elements sequentially. Okay. Down here in our code, what we're going to do is we're going to have every thread be responsible for, so every thread block is going to be responsible for the coarsening factor times the number of threads per block. Okay. So now we've multiplied the elements per block by 4, so we've divided the number of blocks by 4. Okay. So now, yes. So somebody's asking, do we want the coarsening factor to be n over? So somebody asking, should the coarsening factor be such that every thread does the same work as one warp? So no, the warp level scan and the thread level scan are completely different from each other, completely independent from each other, right? Right. We're not replacing warp level segments with thread level segments, right? So like I said, we're going to have over here, every thread is going to scan a segment. Then it's going to put its sum, and then inside over here, we're going to have the warp level scan. Okay, so we haven't gotten rid of the warp level scans. Okay, the warp level scans are based on the warp level segments are based on the size of the warp, which is 32. That's going to be fixed. The thread level segment, it just depends on how much serialization I want to do, right? I can make it 4, I can make it 8, right? Of course, if I'm using shared memory to put that entire block segment, the coarsening factor is going to be limited by how much shared memory I have to put the segment. Okay, so that's why I'm using 4 now, but this is something that you can tune and work with to see what's kind of the best for your implementation. The warp is doing what? Yeah, so each thread is going to scan a segment of size 4 and put the sum of that segment in here in shared memory, and then here what we explained last time is what's going to happen here. Okay. Okay, great. So let's implement this. So first, let's identify where this block segment is going to exist, starts inside of the global memory. So now every thread block, before every thread block was responsible for block dim elements. Now every thread block is responsible for block dim times 4, block dim times the coarsening factor. So let me first define the beginning of the block segment. I'm going to write unsigned int. Block segment is equal to block index.x times block dim.x times the coarsening factor. Okay, so this takes each block to the beginning of the segment in global memory that it's supposed to load. Next, what we're going to do is we want to load this block segment. Now, one important thing here is that we don't want to have each thread load its own thread segment from global memory to shared memory. Why not? So why? So actually, maybe I should ask a more fundamental question, because you're right. We don't have reuse. So we could have every thread go and scan its block segment, right, by loading from global memory into its registers, and we can put this in registers, right? Okay, but why is it not a good idea to have every thread go and scan its thread segment inside of the block segment by accessing global memory directly? What would happen if we do that?
There won't
Let's
be
say
memory
this block
coalescing.
segment is in global memory, and if every thread is going to iterate through its own segment in global memory. So somebody said something online.
Yeah, I was saying the memory accesses won't be coalesced, right?
Right, exactly. The memory accesses will not be coalesced if we do that. Correct? Because if my coarsening factor is 4, for example, thread 0 is going to access the element at index 0. Thread 1 will access the element at index 4. Thread 2 access the element at index 8. So the accesses are not coalesced. Okay? So to achieve coalescing, what we're going to do is we're going to load this block segment from the global memory to the shared memory in a coalesced way. And once it's in shared memory, we are going to do this strided access where each thread is going to do its own sequential scan. Is that clear? Any questions? Okay, so that's
Can you repeat last part?
Excuse me?
Can you repeat what after it's loaded in shared memory, what happens? If it's
So after we load the segment from global memory to shared memory in a coalesced way, right? Each thread is going to go find its own thread segment in shared memory and do a sequential scan of that segment.
okay, fine.
Okay. Okay, so how do I load this block segment in a coalesced way? Right, it doesn't matter which thread's loading what. So we want to assign the threads to the elements in global memory in a way that achieves a coalesced access. So what we do is we have, if I have block dim threads, I will use those block dim threads to load the first block dim elements together, and then the next block dim elements, and then the next block dim elements, and then the next block dim elements. Okay, is that clear? Okay, so that's what we will do. So first is we're going to load to shared memory with coalescing. So I'm going to define a shared memory array. Let me call it buffer underscore s. How big should this array be? The block dim times 4, or the block dim times the coarsening factor.
Okay.
Okay. And now what I want to do is I want to iterate over my block segment and load it in a coalesced way. How many iterations do I need? How many iterations? The coarsening factor, exactly. So I'm going to write a coarsening loop. Okay. What do you think is going to happen to this on loop? What's the compiler going to do to this loop? It's going to unroll it, right? Because the loop bound is constant. So we're going to do buffer underscore s of. So the first iteration, every thread loads to buffer 2 at its index. And the next iteration, every thread loads to its index plus the block dimension, right? And in this iteration 2, every thread loads to index plus 2 times block dimension. Then index plus 3 times
So
block
plus
dimension.
C times block dimension.
Right, exactly. It's going to be plus C times the block dimension. Okay, and that's going to be equal to the input at where, well, first we go to the block segment. And then after we're at the beginning of the block segment, it's the same as the index to the buffer, plus index.x plus C times the block dimension. Is this clear? Okay. So now I've loaded this block segment from the global memory to shared memory. Now every thread can go and start scanning its own segment inside the shared memory. But what do I need to do before the thread starts scanning? I need to do a sync threads, exactly, right? Because the thread is going to be scanning an element that it did not necessarily load. It could be another thread that loaded it, right? So that's why what we're going to do is we're going to include a sync threads right here. Is that clear? Okay, now every thread can scan its own segment. Did you have a question?
Yeah. Wouldn't that
Yes, so you're saying the
thread sum would be almost as large as the initial fragment.
so that the sequential scan does have order n, right? So it's more work efficient than the parallel scan.
The parallel scan, the thread sum, each thread is only taking the thread sum length size would be the block segment over.
Right. So the block now the block segment that I'm still scanning is still blocked in, right? So we still have an n log n phase, right? So the overall work efficiency is still kind of it depends if you coarsen by a factor that's fixed or that's proportional to n. If you always coarsen, so if you always coarsen such that the number of threads running is the number that can run simultaneously. So if I don't have a fixed coarsening factor, if I have a variable coarsening factor that adapts to the input, but sometimes we can't do that because the shared memory is limited, right? Then the log n part is going to be a constant because it's going to be how many threads I can run simultaneously. It will still be work inefficient, but kind of not by an n factor. But usually we can't do that. So usually we're going to have a fixed coarsening factor. Well, not usually, but I mean, it depends how you implement it. But the shared memory is going to prevent you from having an unlimited coarsening factor.
Can't we treat the thread sums as like another layer of block segment and redo the scan thread segment again?
I don't understand.
The thread sum, I consider it like I do another iteration of like thread, taking doing another thread sum
You mean the block scan?
for the thread sum.
So thread sums are already, I'm doing, every thread is doing a sequential scan. It's work efficient.
Yes, so I do another layer of thread doing.
Where do you want to do the other layer? Over here?
Yeah, no, over the thread sum. Thread sum like another block factor.
So you want to do a thread scan in parallel?
Yeah.
But that's not going to be work efficient.
No, coarsen thread.
I don't understand. Maybe ask me offline because I'm not catching on to what you're trying to. Sorry about that. Okay, so now we want to do the thread scan. Well, the thread scan is easy. It's just a sequential scan. Okay, first let me find the index of the thread segment within the block segment. So thread 0 is going to be scanning starting from element 0. Thread 1 is going to be scanning starting from element 4, then the thread 2 at element 8. So in general, because the coarsening factor is 4. So each thread is going to start at its thread index times the coarsening factor. So here, I'm going to write unsigned in thread segment is equal to thread index.x times the coarsening factor. So that takes each thread to its segment within the buffer. Now we can do the scan, the sequential scan. So how do we do a sequential scan? Well, we know how to do a sequential scan. For unsigned int, how many iterations do I need? Just how many iterations do I need to
Coarse
scan
factor.
the coarsening factor? Okay, but element 0 is already what it needs to be. So I'm going to start from element 1 and start adding the elements before. Okay, so we're going to do for unsigned int c equals 1. C is less than the coarsening factor plus c. Buffer underscore s of thread index.x. Sorry, not thread index.x, excuse me. So we're going to go to the thread segment. That takes us to where the segment is, and then plus c. Okay, and we're going to add to that the previous element. So buffer underscore s of thread segment plus c minus 1. Is this clear? Okay, so now every thread did a sequential scan of its thread segment, which is coarsening factor large. Okay. Okay, now that every thread has done its sequential scan, what we need to do is we need to collect the sums of each thread inside of the shared memory. Sorry, no, we don't need to collect inside of shared memory, because when we wrote our block scan, we were providing the block scan with registers, right? And the warps were doing the register scan, and then we were using shared memory within the block scan. So we don't need to collect this in shared memory, right? Every thread is going to call the block scan, but provide it with its thread sum instead. Okay, so let's do that. So now we're going to do the block scan. Okay, so for the block scan, we're going to first extract the sum for each thread. Where do I find the sum for each thread?
Coarsening factor -1.
Right, at the end of the thread segment in the shared memory. So that's going to be buffer underscore s of the thread segment plus the coarsening factor -1.
Should
Okay.
we sync threads, or is this only for the segment?
So what do you
for
think?
the
Do we
thread
need to sync
itself?
threads here?
It's only for the thread itself.
Right, over here, the element that the thread is loading is an element that it wrote, right? In between this step and this step right here, right? No thread is accessing a value that was written by a different thread. Every thread is going to be loading a value that it had written. Okay, so do we need to sync threads? No, we don't. Okay. Yeah, so somebody was asking, do we need a sync thread in between doing the thread level scans? So in between doing the thread level scans, do we need to sync threads over here after doing the thread scans before doing the block scan? And my answer was that over here for the block scan, after each thread does a sequential scan of its segment, it's going to load the sum of its segment from the shared memory to a register. Okay, so we don't need to sync threads there because no thread is accessing a value that the different thread wrote yet. Okay. Okay, so great. So now what we do is we got the thread sum. Now this thread sum is the value that I want to pass to the block scan. Okay, so now I can get rid of this code over here. This is our old code. And here, so here, this value that I was passing to the block scan, this is going to be the thread sum. Okay. Okay, so after I call the block scan on the thread sum, okay, now I've scanned these values using the block scan, and now these values are scanned. Okay, but where are they? They are in the register of the block, correct? So the register of the thread. So now every thread has these scanned warp sums inside of this register that I called thread sum. Okay, so now what do we need to do? Now what we need to do is we need to have every thread get the scanned sum of the previous thread and add it to its own elements, right? So do I need to sync threads over here? Yes. Okay, so now what we're going to do is we're going to have every thread, to be able to have threads get the scanned sum of a previous thread, I'm going to have to put those scanned sums in shared memory, do a sync threads, and then have every thread load the previous scanned sum from shared memory. Okay, so let's do that. So here we're going to collect these scanned sums. So here I'm going to create a shared memory array. How big does it need to be? Every thread is going to have to store one thread sum. So its size is going to be block dim. Okay, so thread sums of block dim. And then every thread is going to write to one element in the thread sum. So what's it going to write? It's thread sum. Okay, so every thread 0 is going to write in shared memory at index 0, thread 1 at index 1, thread 2 at index 2, etc. So now I have written all of these scanned sums to shared memory. What do I do after that before the threads start loading? I have to sync threads, exactly. So I sync threads. Okay, now every thread is going to go to the shared memory and get the sum of the previous thread. So I'm going to have to go and I'm going to add previous threads sum. Okay, So how do I do that? So we did the sync threads. Now, all the threads are going to be active except which thread? Thread 0, right? Thread 0 is already going to have its result. So I'm going to do if thread next.x is greater than 0. Okay, every thread is going to get the sum of the previous thread. So I'm going to write float previous thread sum is equal to thread sums of thread index.x minus 1. And remember when we said that every boundary check that guards it. So here, what's guarding the thread index.minus 1 memory access? The if statement makes sure that thread index.x is greater than 0. Okay, and there's an important rule of thumb. Whenever you have these minus 1s in your memory axes, right, you need to make sure that I have some if statement that's making sure that there's no thread that's going to access from out of bounds. Okay, so here every thread now has went and it got the sum of the previous threads. What does it do now? It's going to iterate through its segment and it's going to add the sum to all of its elements. How many iterations do we have to iterate over the segment? Course factor iterations, right? Is it already 120? So for unsigned int c equals 0, c is less than d course factor plus c. I think we ran a little late because we started a little late because of the technical issues at the beginning. Then we're going to do buffer underscore s of thread segment plus c, right? So every thread is iterating through its thread segment. C is that iteration counter. And what are we going to add to this? Right, the previous thread sum. Okay? So now we're done. Now every thread has added the previous thread sum to its elements. Okay? So now we have this scanned block segment is ready, but it's in shared memory. What do I need to do? I need to write it to global memory. So should I just have every thread directly write its segment to global memory? So should I have every thread iterate through its segment and write it to global memory? No, right, because then that memory access will not be coalesced. Okay, so what should we do instead? We should do what we did with the input, right? We should change how the threads are assigned to the elements and have the threads together store the first block dim elements, then the next block dim elements, then the next block dim elements, etc. Okay, so to do that, I'm going to have to sync threads. Oops. So to do that, I'm going to have to sync threads. And then after I sync threads now, instead of doing this output of I equals val, I'm going to iterate. I'm going to have 4. So here, we're going to write the output. We're going to, for unsigned int c equals 0, c is less than the coarsening factor plus c. And then in each iteration, I'm going to write output of, where am I writing? Starting at the block segment. Okay. And in the first iteration, thread 0 writes element 0, thread 1 writes element 1, thread 2 writes element 2, etc. So plus thread index.x. And then in the next iteration, every thread we add block dim to its index. Next iteration, we add another block dim. Next iteration, we add another block dim. So we're going to have plus c times the block dimension. And that's going to be equal to buffer underscore s of c times the block dimension plus thread index.x. Is this clear? Yeah. Give me a second. I need to plug in. I'm running out of power. Okay, so then we get rid of this. Of course, we also have the step where we have to write the final partial sum. So now the final partial sum can be found in the last element in the buffer. So that's going to be buffer underscore s of the coarsening factor times the block dimension minus 1. It's the very last element in the buffer. Clear? Any questions?
Yes,
Okay.
Professor.
Yes.
What's block scan function?
The block scan function is the function that we wrote last time that does the block level scan.
Warp level. يعني.
Yeah. So the block level scan, if you remember, this is the one we wrote last time. It does a first warp level scan, then it collects the elements in shared memory, then does another warp level scan, then goes back and adds all the elements.
Okay, thanks.
Okay. You're welcome. Okay. There's one more thing. I have this add kernel that I have been using at the block level in order to add. So needs to be modified. So I'm going to quickly modify that. Now, instead of every thread block being responsible, every thread being responsible for adding one element, it has to add 4 elements. So let me just update this one. Okay, and then here, instead of adding 1, it's going to add 4. So 4 unsigned and c equals 0. C is less than the coarsening factor plus c. We're going to do output of block segment plus thread index.x plus c times block dim is equal to. Yes, thank you. Times coarsening factor, the block segment plus thread index plus c times block dim. We add to that the partial sum of the previous block. Okay, we're good. All right, so let's compile this and we'll run it, make sure it works. Okay, and it works. So unfortunately, I don't have the time from the previous implementation, but it's supposed to be better with thread coarsening. Okay, so this is the code that we wrote. Yes.
What was the last kernel you changed for?
I remember I said how we have to consolidate the threads, the block segments across blocks.
Yes.
Right. So that kernel was helping doing that. I'm going to explain what that does.
Oh, okay.
Okay. It's an add kernel. I'll explain shortly what it does.
Okay.
Okay. So all right. So this here is the code that we wrote. Okay. Now one thing we note here, so we applied shared memory tiling, right? Loading this element to shared memory and then iterating over through shared memory. This is shared memory tiling. Okay. However, we notice that here when we are doing this scan, right, we are doing the scan in shared memory, right? So every time when each thread is scanning its segment, it's loading from shared memory, putting back in shared memory, loading from shared memory, putting back in shared memory. And then the final value, we're getting it from shared memory and bringing it back to register. So here, when the thread is scanning this segment right here, every time it's going to load an element from shared memory, put it back in shared memory, load from shared memory, put it back in shared memory. And this final result, it's getting it from shared memory. And then later on, when it wants to do the add, again, it's loading from shared memory, putting back in shared memory, loading from shared memory, putting back in shared memory. So all of these are unnecessary shared memory accesses. Okay. The only reason we needed shared memory here is to be able to convert our memory accesses from uncoalesced accesses to coalesced accesses. So what we can do instead is we load the segment to shared memory just to get the coalescing. But then after that, we're going to get the thread segments from shared memory into the registers and do the sequential scan inside of the registers. Keep that data inside of the registers throughout this entire process. And then later on, get the values from the registers and add to the thread segment while it's still in the registers. And then before we want to store the segment to the global memory, each thread will put its segment inside of the shared memory, and then we write that out in a coalesced way. Okay. So for the sake of time, because we're running out of time a little bit, I won't implement this. But the point is that here we are loading from global memory to shared memory in a coalesced manner. Over here, the threads are accessing the segment from shared memory, and over here we're storing from shared memory we're storing from shared memory to global memory in a coalesced manner. And the point is that these accesses right here, right? The thread is constantly going to shared memory to get its segment, right? That nobody else is accessing. So instead of having these repeated accesses to shared memory, where the thread keeps going and getting its segment from shared memory, what we can do is we can do register tiling, where every thread will place its segment inside of a register instead of putting it inside of shared memory. Okay, I'm not going to do the implementation because it will take some time, and we kind of ran late in the beginning of the class. But the key idea here is that over here we're using, this is the implementation. Over here we're using buffer_s and shared memory to do the load. But then as we are scanning the thread segment, we get it from the shared memory and put it and put the result in here. Buffer_r is a local array. After we do loop unrolling here, this is going to be placed inside of the registers. So when we do the scan, we get from shared memory, but we leave the result in a register. Over here, we're getting the result from a register. So this is just a register to register copy. It's probably going to be optimized by the compiler. And then down here, when we are adding the partial sums, okay, we are going to be adding from the register, adding the partial sum to a value that's already in the register. And then finally, we put the result in shared memory before we write it out to the final. Before we write out the final output. Is this clear? Any questions about this? Okay. So, sorry for running out of time. I would have wanted to implement this, but unfortunately, we're kind of running a little bit. Okay, so one thing to note is that over here, the coarsening factor is going to impact first the buffer that I allocate in shared memory to place the entire segment. And the coarsening factor is also going to impact how many registers I'm going to allocate per thread to store the thread level segment. So here, although having a larger coarsening factor is good for me because it improves work efficiency, I have to make sure not to have a coarsening factor that's too large, such that I would use too much shared memory or too many registers, which would hurt what? My occupancy. Okay, so here, over here, the loop unrolling makes sure that this thread is placed in registers, so we know that. So I just have to make sure that we don't allocate too much so that we hurt our occupancy. Is this clear? Any questions? Okay, so let's go back to our checklist. Right? How many of you have put it on their fridge? Right? I assume everybody by now has it on their fridge. Maybe you have one in your car as well. Okay, so here, let's go through this checklist and make sure that we checked all the boxes when it comes to scan. So occupancy, so I just talked about occupancy, right? We said that when we pick the coarsening factor, we need to make sure not to hurt occupancy because of shared memory. Loop unrolling, well, we saw that these coarsening loops will get unrolled. We also saw that the loops that iterate over the stride 1, stride 2, stride 4, right? We made that loop bound constant, so even those loops will get unrolled. In terms of reducing control divergence, that wasn't too big of an issue for us because with the Koji Stone, the threads drop out from the beginning, right? In the early implementation. In the later implementation, where we used warp level primitives, the stage where all so the stage where we do thread coarsening, all the threads are active. We don't have a problem. The stage where we're using warp level primitives, right? There's a partial warp that's inactive, but that's okay. That's the price we pay to get rid of the synchronization, right? And then the stage where one warp is active, we just have one warp active and all the other warps are inactive. So our control divergence is actually pretty good for scan. For coalescing, before we did thread coarsening, we didn't have a coalescing problem. But then after we did thread coarsening, we had to make sure that we load the block segment and then store the block segment in a coalesced way by using the shared memory. Was there a question online?
Yes. For the first implementation, you mean it's when the warp 0 scans, that's when we have control divergence?
Yes. No, what I was saying is we don't have a lot of control divergence there.
Yes,
we have a little bit within the warp, but all the threads in the warp have to be active because some of them are not adding, but they need to be active when they shuffle. So they're kind of active, but they are not active for the add instruction. So there's some control divergence over there. Okay. Okay, for shared memory tiling, so we use shared memory to put the block segment. Register tiling, we just saw that. We use the register tiling to place the register. So vector loads we could have used, right? When we were loading from global memory to shared memory, we could have used vector loads. To avoid complicating the code, I didn't, but we could do that. For shared memory bank conflicts, we actually do have a bank conflict issue here, right? Because when every thread is loading its segment from the shared memory to the global memory, if my coarsening factor is 4, then threads are going to be loading at strides of 4. So I will have bank conflicts, and I will need to be able to deal with those bank conflicts. That's not something I'm going to do in the class. Again, I don't want to complicate the code, but you can think, on your own about how you can deal with the bank conflicts, either by, introducing some kind of indexing, doing some kind of fancy indexing to be able to avoid the bank conflicts, or maybe picking a coarsening factor that does not result in bank conflicts. Privatization is not applicable because I don't have atomic operations. Warp level primitives, we use those, right? We used those last class in order to reduce the synchronization. Double buffering, we also used that last class in order to reduce the synchronization. And thread coarsening, we also used that in the beginning of this class in order to reduce the work inefficiency of the computation. So as you can see, scan is really a very nice primitive because we almost covered all of the optimizations in our checklist as we are applying scan. Okay, is this clear? Any questions? Okay, so we're done with half of today's lecture, and now we move on to the other half. Okay, and the other half, hopefully the other half is not going to take half the time, right? So I think this half will go faster. So not exactly a half. Okay, so we're done with the first part, and we're going into the second part now. So remember, we said that so far we were doing a segmented scan, and what that meant is every thread block was responsible for scanning part of the global segment in global memory. Okay, and then we were stopping there. And the question is, how do I go and consolidate, right, the segments of the different blocks? Any ideas? We kind of already saw this problem before, right? We saw it when we were decomposing the block segment across threads, and we saw it when we were decomposing the block segment also across warps. Correct? Right. So can we use the same strategy for blocks? When I'm decomposing the global segment, I can decompose it across blocks, have every block do its own segment, right? I can use that same strategy, right? So I can use the same strategy that we used at the warp level and the thread level, where we scan the partial sums and then go back and add the result, okay? But this, remember, between these three phases, at the warp level and the thread level, what did we need to do? We need to have async threads. At the block, right? Can we have async threads? So we have
Sync threads.
Either we have to do a synchronization across the entire grid, but that is going to limit how many blocks can run simultaneously. And if we limit how many blocks can run simultaneously, then we limit the size of the input that we can scan. Because I can't make the coarsening factor infinite because I'll run out of shared memory and registers. Okay? So what we can do, what's another way to be able to make sure that all the blocks are done? We can use 3 separate kernels. Okay? So we launch a kernel. So this is a 3 kernel scan. One thing we could do is we can launch a first kernel that does the block level scan. So every block does a scan, and that's actually what I was doing. And then we can have a second kernel where in the first kernel we write the partial sums of each block inside of an array. We launch a second kernel that does the scan of that array. Okay. And then once we're done with that, we're going to launch a third kernel that goes and does the add operation for each block. So somebody asked me what was that add kernel that I modified. Excuse me. So the add kernel that I modified was that third kernel that was doing this third addition. Is this clear? No? Yes.
Wouldn't this make our work efficiency? This block is in terms of over the number. Let's make our work efficiency.
So you're saying that
before our course, make it doesn't always make it in terms.
We still can't make it in terms of n.
Yes, but treat it as coursening making a lot of repetitive work.
So okay. So I'm glad that you keep bringing up this point. So the coarsening factor is going to be limited because of the shared memory and the registers, right? Which means that if I use the largest possible coarsening factor, After that, as I increase the size of my input, my only option is to increase the number of blocks.
Yeah.
Right? And increasing the number of blocks means they could be serialized, and there is going to be some work inefficiency.
No.
So the work efficiency will still be in terms the work is still going to be in terms of n.
I mean the number of blocks is in terms to the coordinate factor, since we're using the same.
You know what? Let's talk offline because we're kind of I'm already going to keep everybody behind. Over time, I don't want to keep them even longer. Okay. All right. So okay. So here we're using the same strategy, but as we use with warps and threads, but at the block level. We're going to launch a kernel where every block scans a segment, and then every block is going to save the sum of all the elements in the block in memory. We're going to launch another kernel where we do a scan of those block segments, right? We call this the inter-block scan. And then we're going to launch a third kernel that is going to do the additions. Is this clear? Are you sure it's clear? Right? It's the same thing we did at the warp level, but we're doing it at the block level. We have a block. We have a kernel that scans the block segments, a kernel that scans the sums of the blocks, and then a kernel that does the additions. Yes. Yes. Yes, exactly. So I'm glad you mentioned that, because that's exactly one of the issues here. So because we divided this into multiple kernels, what that means is that when we load this global segment from the global memory and we do the scan, what do we need to do with these scanned block segments? We need to put them back in the global memory. And then later on, our next kernel is going to load the sums, scan them, put the sums back in the global memory. And then the later kernel is going to have to go and load all these segments from the global memory again, do the addition, and put all the segments in the global memory again. Okay? And that is the main disadvantage of having this three kernel scan, right? It's the fact that we have to do so many global memory accesses. So let's talk a little bit about the memory bandwidth computation. So scan is memory bound. Do I need to convince you that it's memory bound? Right? I do very little arithmetic compared to the amount of data that I'm getting from global memory. Okay? So the speed of light for performance for scan is going to be related to the amount of data that I will access from global memory. So let's analyze how much data I access from global memory in this three kernel scan approach. Okay, and let's ignore the partial sums. So here the partial sums are very small, right? Every block is going to be responsible for 4,096 elements, but it's only good, and it's going to have one partial sum. Okay, so really the most of the global memory accesses are in these large segments. So if I have n elements, the first kernel is going to load n elements, and it's going to store n elements to global memory. The second kernel, this is going to be n over 4,096, so we can ignore that. The third kernel is going to load n elements, and it's going to store n elements. Okay, so how many global memory, how much global memory accesses do I do in this approach? 4n. Okay, 4n. Okay, so the first kernel does n loads and n stores. That's 2n accesses. The second kernel, we can ignore those. And the third kernel does n loads and n stores. So we have total of 4n memory accesses. And the question is, can we do better than this? Okay. The answer is yes, we can do better than this. So this previous approach at decomposing scan into segments is called the scan-scan-add approach. It's called scan-scan-add because the first kernel does a scan, or the first step does a scan. The second step does a scan, a smaller scan, but it's a scan. And then the third step does an add. There's a different approach that we could do, which is called the reduce scan-scan approach. And let's look at how the reduce scan-scan approach works. Okay, so if I go back, it does, but we can ignore those because the second kernel is scanning the partial sums of the blocks. So every block is going to produce one partial sum. So for every 4,096 elements, I have one value. So this is going to be n over 4,096. It's going to be negligible in our analysis. Okay. Okay. So in the reduce scan-scan approach, what happens is in the first kernel, I'm not going to do a scan. I'm only going to do a reduction. I'm going to do a reduction that's going to find the sum of the elements in the block segment, but it's not going to scan them. Is that clear? Okay. So after I do a reduce, now I have the sum of the elements in each kernel. Next, what I can do is I can do a scan of those sums. That gives me the scanned sums. And then the third kernel, what it can do is I can get the segment again. I add the sum of all the previous elements to the first element in my block segment, and then I scan it. Is that clear? So instead of scanning in the beginning, getting the sum, scanning the sum, and then going back and adding, I'm only gonna do a reduction in the beginning to get the sum. Then I'm gonna scan those sums. Now each thread block has the sum of all the elements in the previous kernels. And now the thread block will do a scan. Okay, so after the thread block finds the sum of all the elements in the previous blocks, that thread block is going to initialize, is going to add that element to its first and scan the rest of its segment to get the scan of the entire block. Is this clear? So what's the difference? The difference in the first case, we did the scan operation here before we had the sum of the previous block elements. Now we're finding the sum of the previous block elements first, and then we are scanning. Okay? Right, so what's the advantage of doing this? Well, let's take a look. In the first kernel, how much data are we loading? N. How much are we storing? N over 4096, that's negligible, right? The second kernel, negligible. In the third kernel, we are loading N, and we are storing N, okay? So we've reduced the amount of data that we transfer between global memory and shared memory from 4N to 3N. So in our 3 kernel reduce scan, the first kernel does N loads, the second kernel is negligible, the third kernel does N loads and N stores, so the total memory accesses are 3N. Is this clear? Any questions? Okay. Can we do even better than this? I apologize, I'm going to take we're going to take around 5 to 10 more minutes just because we started late. Okay, so can we do better than this? What is the speed of light? So what to be able to do a scan operation? What is the minimum number of memory operations that I should do? 2N, right? N loads, N stores. Okay, can I come up with an implementation that does N loads and N stores as opposed, so just 2N as opposed to 3N? If I'm going to use multiple kernels, I can't. If I want to be able to do 2N global memory accesses, my solution is to use one kernel. And to be able to use one kernel, what that means is that I need to have the blocks do the scans and the adds and all these things together, and which means that the blocks are going to have to synchronize, right? So to do better, we need to use a single kernel to avoid having to load the input values twice. So a single kernel scan, to be able to do a single kernel scan, we need to have the interblock scan inside of the same kernel as the segmented scan. We can either do a grid-wide barrier synchronization across all the thread blocks, but that's going to limit how many thread blocks I can launch, which is going to limit the size of the array that I scan. But the question is, do I really need to wait for all the thread blocks? Do all the thread blocks really need to wait for all the other thread blocks? Right. In scan, every thread block only needs to wait for the thread blocks that come before it. It doesn't need to wait for all the thread blocks. So what do we call this kind of synchronization? A unidirectional synchronization, exactly. So we said the grid-wide barrier synchronization is a limit how many thread blocks we can access. So another approach is to do a unidirectional synchronization, right? Where we pass the partial sum from one thread block to the other, and that's going to look like this. So a grid-wide barrier, an interblock scan based on grid-wide barrier synchronization would mean that every block does its segmented scan, and then we do a grid-wide barrier synchronization across all the blocks, and then we have one block scan the partial sums, then we do another grid-wide barrier synchronization, and then all the blocks do an add, right? But this is going to limit how many blocks we can launch, okay? Because with the grid-wide barrier synchronization, all the blocks have to active simultaneously. Alternatively, we can do a unidirectional synchronization. And in a unidirectional synchronization, what we do is every block only waits for the block that comes before it. So here, block 0 is done. Block 1 waits for block 0. Once it has the sum of block 0, it adds it to its elements. Block 2 waits for block 1 and block 0. Once it's done, it gets that result, adds it to its own sum, etc. So we have this kind of synchronization, unidirectional synchronization across the blocks, where every block waits for the previous block to finish. Question? So somebody's asking, how is this not serialization? It is, right? But so remember, there's a block scan that happens at the beginning. That's all happening in parallel. So every block is scanning its segment in parallel. Later on, the blocks are going to add their segments in parallel. The part that's being serialized is the inter-block scan. The scan of the block sums, that is going to end up being serialized across the blocks. Okay? So just to give you an idea, this is what the implementation for this would look like. Here, what's going to happen is you're gonna use an atomic operation to spin lock on a flag and wait for the. So what's going to happen is the blocks. Every block is going to set a flag to indicate that its sum is ready, and the later block is going to wait on that flag to know that the sum is ready, and then it's going to load it from shared memory. So I won't go into the code in details, but the idea is that here you wait on a flag, and then you load the sum from shared memory. You add the sum to your own sum, and then you put that sum in shared memory, and you put that sum in global memory, and you set the flag. Sorry, I said shared memory, I meant global memory. Is this clear? So that's what this code is doing here. And one thing you'll notice is that we're not using relaxed ordering. We're using acquire ordering and release ordering. The reason we use acquire ordering and release ordering is because in the beginning, we are waiting for the block. We are waiting for the flag to be set, and then we are loading something from the global memory. We don't want the compiler to reorder these two operations. So that's why we use acquire semantics. Acquire semantics indicate that you must perform this atomic add operation before performing subsequent memory operations. So the block must wait for the flag to be set before it can load the sum of the previous block. Down here, we're using release semantics. And the reason we use release semantics is because the reason we're doing an atomic operation here is because the block is writing its sum to global memory and then setting a flag for the next block to pick it up. Correct? So we need to make sure that the value that we're writing arrives to the global memory before we set the flag. So here we're telling the system that this global memory write must complete before the atomic operation that sets the flag complete. You cannot reorder these operations. Is this clear? Okay, questions? Okay, so here we're using acquire semantics, and here we're using the release semantics. Now, one thing that we need to do to make sure that this works is we need to make sure that the earlier blocks get scheduled before the later blocks. That's easy to do. Instead of using block index.x, what we're going to do is we're going to have a counter, and every thread block will atomically increment that counter when it starts executing and acquire a block index from the counter. Okay, that makes sure that by using this dynamic ID assignment using an atomic operation, we make sure that earlier blocks with smaller IDs are executing before blocks with later IDs. Okay, so that's what this slide refers to. Okay, so somebody mentioned that this is doing a lot of serialization. And that is the case. And in fact, if we check the performance of this, we find that its performance is terrible. Because even though we are loading from global memory and storing to global memory, right? That serialization that we have across blocks, where every block has to load and then store and then load and then store and then load and then store, and all that is being done atomically, right? That incurs a lot of latency, and the performance ends up to be very bad. Okay, so to overcome this problem, there is an even better approach to making this work. But I know that you're all no longer focusing, so we'll cover that other approach next time. Okay. Okay, any final questions before we end?
Yes, Professor.
Yes.
So here's the atomic add in this slide is from the current version. يعني
Yes,
or-
yeah, sorry, I should have replaced this with a CUDA atomic. I apologize.
okay.
Yeah, these atomic adds are deprecated or going to be deprecated, so it's better to use the CUDA atomics, not these low-level printers. Okay. All right. Well, somebody asked why would they be deprecated. The reason they'd be deprecated is because they're usually bug prone. Because people are not aware of the kind of release semantics versus acquire semantics. So the CUDA atomics make those release and acquire and relaxed and sequential consistency semantics explicit, which is less bug prone. Okay. Okay. So that's all for today. We'll finish up next time, and then we'll move on to talk about a new pattern next time as well, which is filtering. Okay. Bye, everyone. Filtering.